Okay, so welcome again to the to another lecture of the course Fundamentals of Solar Photovoltaics and Technologies. So today we will be in the lecture number 4, in which largely we will be talking about fundamentals of solar radiation. So let's just briefly recap as to what we did in the last class. Last few classes we looked at energy uses and the types of fuels that we use for meeting our energy needs, and we saw that largely they were mainly fossil fuels such as coal, oil, gas and bit of biomass. The problem with fossil fuels is that burning them causes emission of greenhouse gases and variety of other pollutants, which have resulted in many of the dire consequences such as global warming, which is a very important thing. We are already at the brink of 1.5 degrees centigrade increase in global temperature. They have also caused increased frequency of natural disasters, and it is forecasted that if the temperature reaches 2 or 2.5 degree mark, the natural disasters and loss of biodiversity will be far more catastrophic. And this has significant impact on the sustainability of the planet, people and many other species and our whole ecosystem. It will disrupt many of the ways in which we have become dependent in terms of living, and the most affected ones will be the people who are at the bottom of the economic ladder, that is the poor people and other species. But at the same time, while we know the problem, we also know that our energy need is growing, and so the question is, what should we do? Our energy need is growing, but we need to cut down the emissions. So the possible solutions can exist in the use of non-fossil energy sources such as solar energy, wind energy, biomass energy, geothermal energy, even nuclear energy. And among these, solar energy is a very powerful option. Solar energy will not be able to, I don't think we can say that we can totally rely upon solar energy to meet our energy needs, because there are other considerations also, and one of those factors is because solar energy is available only for a certain amount of time during the day, but solar energy is significantly a vital cog in the wheel of our energy sustainability. And among various solar technologies, solar photovoltaics is the most attractive technology, mainly because of its potential to convert solar energy into electricity directly and on demand whenever sun is shining, of course. So solar energy to electricity can be converted in two different ways. One is by the use of heat engines, wherein we convert the solar radiation or the energy which is embedded in solar radiation to heat, and that heat is used in the form of steam to run the steam engines to produce electricity. And basically, by using the principles of a heat pump, we can convert heat embedded in the steam to electricity. This is an attractive process. It has been demonstrated on a commercial scale, but economics of this process has so far been rather difficult. But there are growing reports in countries like China, wherein this process may become a viable process in the future. Second important process, which is already commercial, where a lot of solar installations have come across the world, is solar photovoltaics, wherein we convert the solar energy directly into electricity by the use of what we call as semiconducting materials, which form p-n junctions. So basically, it's a very simple device wherein generally we use a silicon wafer, and that silicon wafer is nothing but a mix of a p and n type silicon. It's a junction of p and n type silicon, and if you make a proper circuit of it and throw incident and expose it to sun, it will produce electricity. And this picture is an example of solar photovoltaic panel, which are installed not only in this place but also all across the world. And so there are arrays of solar photovoltaic panels which can be used to produce electricity at large scale, but you can also use solar photovoltaics at a small scale in the form of calculators and many other small devices. So advantage of solar photovoltaics is it can produce energy from milliwatt level to milliwatt to watt to kilowatt to megawatt to gigawatt. So solar photovoltaics has this beautiful attribute of it, that it can be scaled from very small to very large, and that is what makes it extremely attractive. And there is no other intermediate operation involved in the conversion of solar radiation into electricity. So, just as a brief introduction to solar photovoltaics, basically it converts solar radiation directly into electricity, and thermodynamically speaking the efficiency meaning if you have 100 watts of incident power. So, let us say P in is 100 watt, and if you are able to get output power of 20 watt, then your efficiency will be 20 divided by 100 into 100, that is 20%. So, efficiency of these photovoltaic panels vary anywhere between 8% to 45%, approximately 45%, if not exactly 45%, or 40+% let me say, depending upon the type of technology you use, and these type of technologies depend upon the class of materials that we use. So, there are the photovoltaic technologies are typically divided into 3 classes or variants. The first one is wafer based technology, which came about soon after discovery of p-n junction, which is based on silicon wafer based technology or gallium arsenide based technology, which is silicon single crystal or polycrystalline based technology, and this is oldest commercial technology and a very successful one. Right now more than 90% of the solar installations across the world are based on silicon based technologies, and these use wafer which is a thin silicon piece of roughly 0.2 to 0.4 millimeter thickness. Okay. So, there is a lot of material which is used. You do not require actually this much amount of material to absorb the light, but this is what it is right now. There are other technologies which are second generation technologies which are based on thin films of variety of materials. It could be amorphous silicon, gallium arsenide, thin film silicon, cadmium telluride, copper indium gallium selenide, and organic solar cell is a third generation technology, or dye sensitized solar cell or perovskite solar cells. These technologies again yield efficiencies anywhere from 7-8% to about 27% at the moment, depending upon the type of material and technology. Silicon on the other hand has already reached about 27%, that is at the lab scale in the single crystal silicon. Gallium arsenide of course is higher than silicon, but gallium arsenide is something which is not used on a commercial basis because of its cost. Third variant could be multi-junction technologies, wherein you use different materials, put them in one solar cell, so that you are able to harness better part of solar energy and convert into electricity at a higher efficiency, typically more than 30%. And then there are some new technologies such as quantum dots or plasmonic solar cells, which are right now at the research level. They have not become commercialized yet. So, all these new technologies which are here, with the exception of cadmium telluride, which is a stiff competitor to silicon. So, this is silicon is commercial and cadmium telluride is commercial, and this is more than 90%, in fact more than 95% I would say, and rest is cadmium telluride. All other technologies, some of them have been brought closer to commercialization, but they are not successful as yet. But technologies like organic solar cells, perovskite solar cells, multi-junction solar cells, they are still not yet commercial because economics does not work out yet, or they have certain issues which prevent them from becoming economical. The other technologies face a stiff competition from silicon, but nevertheless silicon technology itself is a very successful technology. So, the way it works is, it is a very simple concept. You have a device which is basically a silicon wafer. So, you can say this combination of red and blue is a silicon wafer. On top what we have is a emitter, which is, you can say, n type silicon. Typically on bottom we have p type silicon. So, it is a junction of n silicon on top of p silicon, and then on the top and bottom we have metal contacts. The rear side is totally coated with the rear contact, or it may be partially coated, but the front side has to be necessarily partially coated with silicon with the front contact, and you shine this to light the areas which are not covered with metal. The light is absorbed in those regions, then light creates a electron hole pair, which we will see later on what they are. So, a photon of solar energy creates an electron hole pair, and this electron and hole pair, they move to respective electrodes to provide you the electricity or the power. and this whole solar cell is connected to an external load which helps you in extracting the maximum power under certain conditions. So, basically it is a very simple device, just a wafer sandwiched between two electrodes and connected to external load, which is when exposed to light produces electricity. And this is what makes solar photovoltaics very beautiful, because it is a very simple and neat concept. So, across the world a lot of research has been done since 1950s, but accelerated in 1960s and 70s due to space race between Russia and US. So, you can see that the oldest technology being the blue one, which is basically silicon based technology. So, this is silicon, and then some other technologies are cadmium telluride and copper indium gallium selenide. So, this is CDTE, this is CIGS, and this one is again amorphous silicon. So, research is still continuing on silicon, cadmium telluride and CIGS, which have achieved efficiencies of the order of 27.8% for silicon, and then for cadmium telluride it is 23.1%, and for CIGS it is about 23.6%. But in around 2010, after the discovery of new materials such as organic materials and perovskite materials, some new materials have come on the block, and you can see that right now we have a very interesting material called as perovskite, which gives us efficiency of nearly 27% at the lab scale, and another material is organic solar cell, organic materials which are here at the, and this organic material has efficiency of 19.2%. So, these are some interesting technologies on which the work is going on, and you can see if you combine many different materials together, you can achieve efficiencies of the order of anywhere more than 30%. So, these are all you can say multi-junction solar cells, where you put different materials together to harness the band gap. So, efficiencies on a lab level have reached up to 47.6%, but most of the single junction technologies, which is what commercial technologies, they are below 30%. Silicon is for example 27.8%, but perovskite is a close competitor, which is a very research intensive technology at the moment, which has already reached 27%. So, we will talk about these technologies in the due course when we talk about materials and technologies, but this is the state of the art that we have at the lab level across the world. On a commercial level, we have silicon technology whose modules are 20+% readily available. So, we have modules 20 to 24% efficiency available commercially. Similarly, we have cadmium telluride modules which are about 20% efficient. They are commercially successful modules, and we will learn about these technologies in the due course. So, so far this was the introduction part, and what we have learnt is that if we use solar energy, we can directly convert it into electricity using solar photovoltaics. The principles of solar photovoltaics we will learn later, but first and foremost thing is what is solar radiation and how do we measure it, because in order to quantify the performance of a solar cell, we must first quantify the solar radiation itself. So, the questions are, how do we determine solar radiation, or how do we assess the solar radiation, how do we quantify it, and how do we measure it. So, we will learn about certain characteristics of the solar radiation in this lecture, in the remaining part of this lecture. So, some basic properties about radiation that we got to know. First is called as photon flux. Photon flux is number of photons that are incident per meter square or per unit area per unit time, that is given as NPH per meter square per second. Okay. Second important thing about a photon is its energy. The energy of a photon is given as E, which is hc divided by lambda, or you can say h nu. So, let us say if you have a wavelength of 1 micron, you can, if you multiply Planck's constant and speed of light, it gives you energy of about 1.24 electron volt, and 1 electron volt is equal to 1.6 into 10 to the minus 19 joules, and which is nothing but charge of electron essentially. Third important thing is incident radiation, which is typically depicted as H and expressed in watt per meter square, which is the energy incident per unit area per unit time, and this is flux multiplied by the energy, and this is basically the product of two quantities, and you can work out the units. So, joule per second will give you watt per meter square. So, watt per meter square. So, the question is, can we calculate the incident radiation for a wavelength of 1 micron, and let us say the photon flux that is incident on a surface is 1 into 10 to the power 21 per meter square second. So, if we do that, we can quickly work it out. H is equal to the photon flux, that is 1 into 10 to the power 21 multiplied by Hc upon lambda. So, you put in the value of H, put in the value of C, that is 3 into 10 to the power 8 meter per second, divided by the wavelength, that is 1 into 10 to the power minus 6 meter, and you get an answer which is 198 watts per meter square. So, at this wavelength we will have so much of incident radiation. So, these are certain numbers that you must know how to determine. We consider typically sun as a black body which is maintained at 5800 Kelvin at its outer surface. We know that black body is a perfect emitter, and it decides the upper limit of emission from a body, and the energy that it emits is a function of temperature of this body. So, the monochromatic emissive power, that is the rate of energy emission per unit area for a particular wavelength, can be expressed as it can be expressed by Planck's law. So, we can say energy density of radiation emitted by a perfect black body is given as EB lambda, lambda subscript meaning for a particular wavelength is equal to C1, a constant, divided by exponential of C2 by lambda t minus 1, the whole thing multiplied by lambda to the power 5 into n square, watt per meter square micron for a given wavelength. This is called as Planck's law, and if you integrate it for all the wavelengths from 0 to infinity, what we get is basically, if you integrate EB lambda for all the lambdas, that is 0 to infinity, what we get is basically Stefan-Boltzmann relation, that is EB is equal to sigma t to the power 4. This is what you must have read at the school level. Stefan-Boltzmann law says that the energy emitted, total energy emitted from a black body is sigma into t to the power 4, where T is the temperature of the body and sigma is the Stefan-Boltzmann constant, which is given on the right in the slide. So, this is the amount of energy which is emitted by a black body, which is dependent upon Stefan-Boltzmann constant and its temperature. So, for the sun at 5800 degrees centigrade, we can determine how much the energy will be for a given temperature. So, if you look at sun is essentially 90% of hydrogen, 9% of helium and 1% of many other trace elements. And the most important reaction that at the sun is 4 hydrogen atoms, they get converted into 4 helium atoms and produce a lot of energy, and this energy is 26.7 mega electron volt. This is a huge amount of energy. Scientists have been trying to replicate this reaction in the lab. There have been some success in this direction, but this is an immensely challenging reaction to carry out in at the lab scale, because it is such a powerful energy producing reaction. So, sun produces a lot of energy. Our concerns are living on earth, how much is the amount of energy we get at a given location. Does it vary as a function of wavelength? Does it vary as a function of time of the year? And does it vary as a function of time of the day? And it does. So, that is what we are going to learn. How does this energy that is incident upon the earth by the sun varies as a function of some of these factors which we encounter in day-to-day life and which will affect the performance of a solar photovoltaic device. So, let us first look at the relationship between the sun and the earth. You can see here that on this picture that sun has a radius of 6.96 into 10 to the power 8 meters. Earth is much more smaller as in comparison. It has it's about 3 orders of magnitude smaller. The distance between sun and earth is about 1.5 into 10 to the power 11 meters. Sun, at its core, it has a temperature of about 20 into 10 to the power 6 Kelvin, which is huge, massive temperature. And the coldest part of the sun is the outer surface, which we assume as a black body. It is at about 5800 Kelvin. So, emitted power density from sun is about 64. You can see it's 64 million watts per meter square at 5800 Kelvin, and this is at a peak wavelength of 0.5 microns, a huge amount of energy. The rate of energy emission from sun as a consequence is about 3.8 into 23 kilowatts, and the energy that we intercept, because we are much smaller as compared to sun. So, the energy that is intercepted, so sun is basically emitting like this. So, the energy that is intercepted by us is very small, because we are much more smaller as compared to sun. So, energy intercepted is about 1.7 into 10 to the 14 kilowatts, which is nearly, you can say, 9 orders of magnitude smaller as compared to energy which is emitted by sun. But even then it is a very, very large number. So, if you look at solar irradiance curve, which plots solar irradiance, that is watt per meter square for every wavelength. So, that is why watt per meter square per nanometer. On the y axis we have solar irradiance, on the x axis we have wavelength, which is in nanometer. So, it shows that solar irradiance vary in this fashion. So, it increases from about 200 nanometers, maximizes at about 500 nanometer, and then goes down before it becomes very low at very, very long wavelengths. So, typically you will see the sunlight at the intensity of light or a spectral irradiance will be very high at the top of the atmosphere, but as you come from top of the atmosphere towards the earth at the sea level, there are a lot of atmospheric constituents present, and this, as a result, there is a drop in the spectral intensity. You can see that the yellow part, which can be modeled as a black body spectrum at 5250 degrees centigrade. The magnitude of spectral irradiance decreases. It is now shown by the red curve. So, you can see there is a significant drop in the spectral irradiance as we come to at the sea level, and this is because of atmospheric constituents that are present in the outer atmosphere of the earth, and we will see how these losses occur in due course of time. So, basically we can say that the mean extraterrestrial, so you can see that there is a range over which this spectral irradiance occurs. It starts from about 200 nanometers and it goes until about 2500 3000 nanometers, and there is a wavelength dependence also. Typically we divide this irradiance plot into three regions. So, let us say there is a middle region which is from about 0.35 350 nanometers to about, you can say, 700 nanometers. This is the visible region. The one below that is called as UV ultraviolet region, and the one above that at higher wavelengths is called as infrared region. And if you make approximation, then mean extraterrestrial irradiance, that is normal to solar beam, which is on the outer fringes of Earth's atmosphere. So, you have Earth, then atmosphere, the outer fringe of that atmosphere, the mean irradiance that is incident upon that point is 1.35 kilowatts per meter square. So, this is an important number, 1.35 kilowatts per meter square, that is, you can say, the mean irradiance, you can say that is H bar, okay, or 1350 watt per meter square. So, you will see that this number is approximately written in different ways, but approximately 1350 watt per meter square. So, for solar cells we generally focus on the region which is from about 300 nanometers or 350 nanometers until about 1000 nanometer, whereas for conversion into heat, because heat requires the infrared part of it, we can extend up to about 3000 nanometer for conversion of infrared into heat. But for solar cells purposes, we are generally limited to visible into IR region, that is from about 300 nanometers until about 800 or 1000 nanometers. So, you can see that roughly 20, so you have lot of energy which is incident on earth, 23% gets absorbed in atmosphere by atmospheric gases or dust or other particles, 29% is in the form of, it gets reflected, cloud, bright surfaces, atmosphere itself, and the remaining, so you can see this is 23 plus 29 is, you can say, is about 52%, and remaining 48% comes down, okay. So, let us break this up in this here. So, average incident solar energy on Earth's surface outside of Earth's atmosphere is about 342 watts per meter square, okay, roughly twice to that of the number that we have shown earlier. Let us say we take that as 100%. Okay. So, 29% of that, or 100 watt per meter square, is the energy which is scattered or reflected back to space by the atmosphere and Earth's surface. So, 6% of that is generally scattered by air, water vapor or aerosols in the atmosphere, 20% is reflected by the clouds, and 3% is reflected by Earth's surface. 71% is incident onto Earth's atmosphere, that is 252 watts per meter square. Out of that, 23% is absorbed by the atmosphere and clouds, remaining 48% is what is absorbed at the Earth's surface, and that is what is the number that we saw earlier, that 1.35 kilowatt per meter square. So, 48% of 342 watt per meter square will be what is incident on the outer atmosphere of the Earth, on the Earth's surface. That is, so this basically consists of variety of shorter wavelength radiation, and this is what is absorbed by whatever is present on us, that is land, water or vegetation. So, this is another plot of the energy balance or power balance. Incoming solar is about 174 petawatts, 10 is reflected by atmosphere, 35 is reflected by clouds, 7 is reflected by Earth's surface, 33 out of this is absorbed by the atmosphere, remaining goes into the Earth, but lot of this is again re-radiated into space. So, you can say about 111 is radiated to space from the atmosphere and about 10 is radiated from Earth to space. So, nearly 89 petawatts is absorbed by land and oceans, which can be converted into per meter square, which is 1.35 kilowatts per meter square. What we get is basically electromagnetic radiation. As we know that every object, when it is more than at a temperature more than 0 Kelvin, it emits radiation, and radiation is all across all the frequencies, and here the spectrum will contain all sorts of frequencies, but the largest part of the spectrum lies in visible spectrum, and this visible spectrum is from about 350 nanometers to about 750 or 800 nanometers. So, the ones which lie on the left hand side, that is in the blue region, are called as high energy photons, and the ones on the right side of it are called as low energy photons or red wavelengths. So, on the right of, as you move towards higher wavelength, you will decrease the frequency as well as the energy of the photons, and the UV vis IR region, in which generally we are interested for solar energy application, lie somewhere between 0.15 to 3 micron, but more precisely speaking, for most materials it will be from 300 nanometers to about 1 micron. And this is, solar energy undergoes variety of absorption in the atmosphere. So, roughly 5% of radiation will be in ultraviolet region, 43% will be in visible light, and nearly 52% will be in the infrared region. And there are, you can see that as it comes down to the sea level, there are absorptions, and these absorptions or losses that happen are because of various constituents such as water vapor, carbon dioxide, ozone, and many other greenhouse gases. And you can see absorption bands of, for example, for water, this is H2 absorption band, this is also H2 absorption band, this is carbon dioxide absorption band. So, there are the absorption band which can be seen in the absorption spectra of these of the solar irradiance curve. So, basically the important parameters that we consider for determination of solar radiation are, first, the radiant power density from sun. So, how much power is incident on Earth from the sun. What is the spectral distribution, which means how does this intensity of radiation, spectral radiance varies as a function of wavelength. How does it vary as a function of time during the day or the year at a given location. There is a location dependence also, there is a time dependence also, and then does it also vary as a function of incidence angle. So, what is its dependence upon the angle of incidence on a given surface, or in this case on the surface of P module. These are the questions that we will answer in the next class. So, we will stop here. So, in this class we have discovered a little bit about solar photovoltaics introduction, and also a little bit about the solar radiation. We will look at in the next class the losses that occur in solar radiation, and a few geometric parameters or which are important to understand for estimating the solar radiation correctly on a given location on a PV module. Thank you very much.